Okay, so this is our first YouTube video that we're going to watch in class, and this one is on the kinematics equations. I want to give a couple of notes before we start. One of the most important things I want you guys to know about this concept here is that I really want to try to maximize and be efficient with our time, as well as to try to work on some learning concepts. The idea that you can go search and find information by yourselves, especially online, rather than me give like a single lecture to 30 students a couple times a day. What's maybe more efficient is for me to make the lecture once, post it to YouTube, and then you can go watch this, and you can do this asynchronously. And what that means is if you're doing it asynchronously, you have the ability to pause this video. You have the ability to fast forward if you really wanted to. You can stop. You can rewind. For example, if we do some calculations in a bit here and you weren't able to get the right number, you can stop the video and keep going. And that's something we can't do in a class on a whole because we kind of move at kind of the same pace altogether. So this gives you a little more flexibility in that. And hopefully what it'll also do is give me some flexibility to be able to come around and have some more conversations with you and be able to work with you guys in one-on-one settings when you do have questions. So what I'm hoping for is that you currently are, I mean, if you're watching this video, you've clearly gotten this far, that you've got a device like an iPod or an iPad or a tablet or a laptop or whatever, right? And you've also got some headphones so that you can listen by yourself and not have my voice, being broadcast 30 times in the classroom. And then what you also got, though, is the notes printed off. That's really important. Go to the Learning Commons and print these notes off for you so that you can take notes and you can write in the margins. That's really key. When I've got like open area, over here, sometimes I'm going to be writing things there. And it's going to be really key for you to basically follow along. That's kind of the goal. Okay. So anyways, without further ado, let's get started on our first topic. And if you have any questions, if you get stuck at any point along the way, don't forget, right? I mean, I am in the room right now, hopefully I'm in the room right now as you're watching this. And stop me, right? Pause the video, stop me, and ask me to come clarify. But this gives you the chance to work a little bit more independently. And that's something that I think is a really useful skill and something that I think education is going to go towards in terms of technology being useful. So let's get started. What you have hopefully learned so far about physics is that physics involves a lot of quantitative data. I'm going to write that out here. Quantitative. There we go. Took a while. And quantitative data means there's a lot of numbers. There's a lot of measurements. And there are 4 different things that we've already learned how to measure. There's distance, which we represent with a D, or it's vector doppelganger displacement, which we put a little arrow hat on top. And displacement just means you have a direction. Speed and velocity work the same way. It's just a velocity. You need to know which direction you're traveling. Acceleration is usually considered a vector because you need to know whether or not you're accelerating north, south, east, or west. And that means you could be speeding up or slowing down. And then finally there's time, which is measured with t, and that's not a vector. And so there are 3 things here that are vectors, right? The acceleration, the velocity, and the displacement, where you need to know which direction really matters. Right? And there are 3 things, distance, speed, and time, where we don't really have the ability to tell you which direction. For example, in time, right? You can't put a direction on time. Or we're just choosing not to. Like for a distance, I just might say that this classroom is 20 meters across. And there's really no north, south, east, or west, but I could tell you that you walked 20 meters. That's not displacement. With that, you should hopefully know a couple of formulas already. One of them is the V equals D over T formula. And this may involve vectors, so I'll throw the little vector hats on top. And this is something known as uniform motion. Uniform motion. Or you're always going the same speed. Whereas the other formula that hopefully you're familiar with is your acceleration is your velocity over time. And this is non-uniform motion. Because one of 3 things is happening here. Non-uniform motion versus uniform motion. Okay, I said 3 things are happening here. I want to get to that in a second. I do want to point out that though this often involves the change in displacement and the change in velocity over the change in time. Sometimes you see those little delta symbols. So if you're not familiar with that, this triangle is known as a delta, and it's the Greek letter which refers to changing things. So anyways, let me talk about acceleration. There are 3 main things that acceleration can do. I'm not going to write them out because I'm just saying it verbally, but you can have something speed up, So you could increase its speed. You could slow it down. It could be decreasing its speed. Or you can also change its direction. And this is something that we're going to cover a little later in the course. But you can actually have acceleration if something all of a sudden is still going the same speed but starts going in a circle. And we call that centripetal acceleration. You probably felt this before if you're in a vehicle that's taking a corner a little bit too fast and you kind of get thrown into the door maybe. So, okay, let's use some of the new formulas. These are going to be your main kinematics formulas. They're what we're going to spend the next couple of weeks focusing on. And again, we've already learned 2 of these formulas. One really important note, this top formula right here though, the V equals D over T formula, it is only allowed if you have uniform motion. If you don't have uniform motion, you can't use this top formula because it would mean you're accelerating. And you notice that all the rest of these formulas here involve an acceleration. Or if they don't involve an acceleration, they involve 2 different velocities. The velocity final and the velocity initial. Okay. So if you haven't seen those before, that's what the little subscripts refer to. The I is initial and the F is for final. And really, we're just going to spend the rest of this particular lesson. This is where I lose but today, if you get lost, pause the video, pause this over, and I'll maybe help out. Or rewind the video, right? And we'll watch it. Trying to kind of troubleshoot about solving. So you're going to write down variables. We know that the acceleration out of the first block is 4. And this is my little thing. We've also write a V here for speed, and it was 2.0 meters per second. But I don't know whether it's initial or final, and it said it's going to slow down to a speed. That little word right there, to a speed, lets me know this is going to be my final velocity. And the last question just says, well, what's your stopping distance? And so putting all this together, what we end up getting then is this formula here. D equals VFT. And then if you go back to the previous slide, just to double check, it's VFT minus 1/2 AT squared. This is this formula right here that we're using. So with that being said then, there's 2 main ways of solving this. The first way of solving is just to kind of plug in some numbers. And so I'm going to do that here. I'm going to take my distance, which I don't know, and I'm going to leave it blank, and I'm going to plug in the VF, so velocity final was 2. I'm going to multiply it by time, which is 20. I'm going to subtract 1/2 of my acceleration, which is negative 4.5, and I'll times that by 20 squared, and I'll get an answer. And that is one of the ways you can do this, and really it's actually the only way you're going to solve this particular formula. Sometimes you have to do some algebra, though, and do some rearranging, and I'm going to show you how to do that on the next example. So this one's pretty straightforward. Take your calculator, type it in, and if you're not able to get the answer 940, which will be in meters, let me know, and I'll kind of try to come help make sure you know how to use your calculator properly. But this one's pretty straightforward. Just plug her in your formula, you're good to go. The last thing we should talk about, though, is something called significant digits. And I did a lesson on this with our measurement section. But this number right here has 2 significant digits. The 2.0 has 2 significant digits. The number 20 is a little ambiguous. It could have had 1 sig dig or 2. It's really uncertain as to whether it's rounded to the nearest ones of a second or tens of a second. But I think in this case here, normally what we're going to do is if we see a 0 ending a trailing 0, we'll count it as a sig dig. So I believe we need 2 sig digs, which means this one right here we should really change to this. 9.4 E2 meters. The E meaning times 10 to the 2. And so again, if you're lost on that and you don't understand where that came from, pause the video and ask for some help. But I'm going to move on to the next question. So this actually is a very similar sort of scenario. We're actually slowing down. There's a parachuter. He's going to deploy his parachute 1.53 kilometers above the ground. He's going to decelerate. So again, it's going to need a acceleration value, but it's really negative 6.3 meters per second squared. And meters per second kind of means the same thing. So we're also given a time value this time, so 0.71 seconds. And well, this is where we get a little stuck. It says he travels 34 meters, which is a distance. But wait, this 1.53 kilometers is also a distance. So that's a little perplexing, right? What do I do when I got two distances? And this is really the essence of physics, is that it's not just math. Yes, math is a big part of what we do, but a lot of it is problem solving and understanding scenarios and being able to interpret what's going on. And in this scenario here, he's 1.53 kilometers above the ground, but that doesn't matter because his parachute is going to take just under a second to deploy. And I mean, he's still going to be falling down, right? Like, he's still going to fall down as this parachute starts popping out of his backpack and it inflates, right? So the distance he's actually traveling is that 34 meters. And that's part of the challenge, is it won't necessarily tell you which numbers to use. You have to have your own logic and reasoning. It wants to know the man's velocity when he initially opened the parachute, so that's VI, which means I need a different formula. I need a slightly different one. I need the formula that goes D equals VIT, what is it, plus or minus? Plus 1/2 AT squared. Now I'm going to point out one of the nice things about me being able to make this video in advance is I'm not going to be waiting a whole lot. Okay, I'm just going to keep plowing through examples. So if you need to pause, right, pause the video for your wait time, right? But unlike class where I would kind of, wait a minute or two for everyone to catch up, I'm just going to keep going, right? So if you fall behind, press pause, right? So anyways, here's where you have two main ways of doing this. You could plug some numbers in. You could plug in while distance is 34. Velocity initial is what we're looking for. It needs to get multiplied by 0.71. Then you can add to it 1/2 of your acceleration, which is negative 6.3, and times by your time, which was 0.71 a second time. And then you can just solve this using your algebra skills, but like with numbers in place. And so what I might do here is make this 34. I might rearrange this and make it 0.71 VI. And then I'm going to solve for what this value here is. I'm going to take 1/2 of 6.3 and 0.71 squared, and I'm going to discover, to do this right though, that this whole number here is the number 1.587915. And so then I'm going to add this number, that's an add sign, 1.587915. I'm going to add it to both sides, which gives me 35.587915. And yes, it is important to keep all those digits. Do not round until you are done. Super important. And then for the last step, divide by 0.71. And again, I'm kind of blitzing through the math here a little bit. It's kind of an expectation that you've taken some math courses before. I mean, ideally, math 20-1 is kind of a prerequisite. 20-2 works as well. But I mean, this is not algebra that you need to do in math 20. This is grade 10, grade 9 algebra. But if you're stuck, please let me know. I end up getting 50 meters per second, which actually makes sense because that's about terminal velocity for an object falling. So if you end up getting to terminal velocity, that kind of makes sense. 50 meters per second is about when things can't speed up anymore, and that would make sense as to when he opened his parachute. So if I lost you there, make sure you let me know, and I will try to help. But I want to show you another way you could solve this. What you could do is just do all of your rearranging before you type your numbers in. And this is probably the preferred method, right? Because what we need to do is we need to isolate math-wise for VI. So again, big math skills, right? Physics is not just about math, but like it is a big component of this. So I'm going to rearrange by taking D and subtracting 1/2 of AT squared to the other side. So I'm going to bring that to the other side. I'm going to divide by T again. That's going to give what VI was. So if you can follow how I pulled that off, I took this term and subtracted it over here, and then I divided out the time value. Well, now I have a new formula for VI. I can just do this all in one step. It'll be 34 minus a half of, was acceleration, negative 6.3, 0.71 gets squared. Divide this all again by 0.71. And as long as you know how to like type this in your calculator and do this properly, you can just do this all in one big. Now, if I can give some advice, you need to make sure that you calculate your numerator, which is this whole top part right here, independently from your denominator, and then divide them. Don't type this all in one big line. Calculate a numerator, get an answer, and then divide. So it's 34 minus a half times negative 6.3 times by 0.71 squared. And I pressed enter on my calculator to get 35.587915. Then divide by 0.71. And again, I get the same answer of 50. And that we would consider to have two significant digits, which matches what we need, which is the same I got last time. So there. So one thing that I want you to see between these two examples, the first example we did, was more or less just plug the numbers into the formula. And I need to point out, when you guys have to show your work on written questions, which is your assignments, I want you to show your work. I need you to put those numbers in and show that, okay? That is part of the written response rubric. And more importantly than that, these are good skills to build up now while this is new. If you try to work on this now, you'll build healthy habits, because I promise you it's going to get more challenging and more difficult as we go along. We're really learning 6 formulas off your formula sheet, right? There are 6 formulas here. But if you look at your whole formula sheet, there are like 100 on there. And so over time, it's going to be worthwhile to make sure that it's clear what number, right? This number went there, this number went there. There's nothing worse than making a calculation error. So, I mean, not only is it good, healthy practice for written response, but it's a good habit to build right now, is to just kind of show your work. Right? Don't just do it all in your calculator. I will not be able to give you full marks. One more thing is the difference between this example and the one before it is that the first example was more or less just plug her right in, right? Second example, though, we had to rearrange algebraically. So let's try a third one here. We've got a bullet accelerating the length of a barrel of a gun 75 centimeters. Well, to me, that screams that's a distance or displacement, 75 centimeters. We have a magnitude, and I believe that that's still referring to its acceleration. And this time it's speeding up, so we're going to use a positive 5.35 E5 meters per second squared, right? So there's that one. That's the acceleration. And it wants to know with what speed the bullet, this should be a bullet with a T. So we want to know the final speed the bullet leaves the barrel. Well, on this particular question here, it feels like there's not enough information because I've only given you 3 variables. What formula can we possibly use with distance, acceleration, and solve for a velocity final? But it's hidden, it's sneaky. This is, again, part of that problem-solving bit, is that when you shoot the bullet the first time, the bullet wasn't moving before it started. And so we actually do know the velocity initial was 0. There was no initial velocity before we began. So if that makes sense, that's awesome. If not, maybe pause and ask Chris to elaborate on this. But now we've got to figure out a formula that involves a distance and acceleration, two velocities. And the formula we're going to use now is this one right here. Vf squared equals Vi squared plus 2AD. So I'm going to start by writing out the formula. Vf squared equals Vi squared plus 2AD. And this particular time, I think I'm going to want to rearrange the formula for Vi. So to rearrange this formula for Vi, I'm going to need to do Vf squared. I'm going to have to minus the 2AD from this right-hand side over here to the left-hand side. And then because it's Vi squared, I'm going to have to square root when I'm done. And now I've made myself a formula for Vi. Right? And that works. If you need to type numbers in and do it piece by piece, that's fine too. But I think it's going to look something like this. Oh, I totally messed up, didn't I? Look at this. We were looking for VF, weren't we? This is so silly. We were looking for VF, and I rearranged for VI. Yeah, this happens. I make mistakes too. So ignore the whole thing, because this is actually one of the easier ones, right? We're looking for VF. So it was VF squared equals VI squared plus 2AD. And as I look at this here, to get VF by itself, all we had to do is actually square root both sides. So let's just make sure that formula was right. Yep, Vf squared is Vi squared, so all we had to do is to square root both sides. That was silly. Okay, so here's our formula. Vf will be equal to our initial velocity squared. Well, that's 0 squared. Plus 2 times my acceleration. Okay, well, this time it's positive, though, right? So 5.35 times 10 to the 5. And what I'm trying to illustrate on this particular example, though, is the distance. You can't just type in 75, because that was 75 centimeters. So this is where you need to know your prefixes. A centimeter is a 10 to the minus 2. You have to make sure that you convert that centimeters into meters. Now, I mean, you could write it as 0.75 if you like, but I think my preferred way of doing this is just knowing that a centa, a C, is a times 10 to the minus 2 value. And you can just find that on that one chart that I gave you in our notes the other day. It's also on your data. So now this is really, again, just plugging numbers in. So 2 times 5.35 times 10 to the 5 times 75 times 10 to the minus 2. And when we square root the whole answer, I get this answer here. And with significant digits, we're going to have to round in a bit, but I got 895.8, and that'll be meters per second. But we're going to need to round this to what looks like 2 sig digs, because 75 gets 2 sig digs, which means I only get to keep the 8 and the 9, and really the 5 is going to round up. So this is when we're done going to be 9.0 times 10 to the 2 meters per second. There's my solution. Now, there's no wait time when I do a video like this, right? The expectation is that right? So that means that that's the beauty of a non-asynchronous. Actually, the next slide is kind of a way really but the final formula, the V equals D over T formula, so change in velocity. We have 2 different velocities that are changing. 5 main formulas. And the way it basically works, variable. Solve for the missing one. And that's what we're going to kind of do on the next example here. So on this one right here, study wet and dry circulation are between 24.2 and 23.3 feet per second. And I've thrown like a little twist in here, though. We need to convert feet and meters between each other, which is a little bit annoying here. So I have put a little conversion ratio. There is this many meters in a foot. And so it says that we're driving at 100 kilometers an hour. We'd like to figure out the difference in stopping distance between wet and dry conditions if you have 2.3 seconds before a collision. So the way this one's going to work then is, let's start writing down some of the things we know. We know an acceleration rate. We actually know 2 of them. We know the wet is negative 24.2 per second squared. And we know the dry one is 23.3. And we need to be able to convert that into meters per second at some point. We also get to know our initial speed. Our initial speed in either case was 100 kilometers per hour. And you'll notice that like these units, they don't match up at all. We are being asked to find the stopping distance. And the time value is 2.3 seconds in order to stop. Right? You have 2.3 seconds before a collision. So this formula is actually this one, and I'm going to save a little time on this one here. For instance, stopping. Here's what makes this question challenging, is that the units, do some converting of units before we plug numbers in. So, first thought, convert that feet per second to like meters per second. So here's what I might go kind of need to go off to the side here. I'm going to take feet per second. And it says that there are 3048 meters in a foot. So that I multiply it. I now have 7 meters. I now have the appropriate value. And what you want to write in the margin of the column here, because I have to do this now. Same math here, 23 feet. Gives me a deceleration rate, because we're slowing down, right? Deceleration of 7.10184 meters per second squared. Right? Honestly, I should probably just erase all of this work I have here, because none of it's any good yet. So let's just save some space. I will save the bottom part here, though. There's one more number we have to convert. It gave me 100 kilometers an hour. So I'll use a third color here. It gave me 100 kilometers an hour. Well, that's no good either. So, I mean, here's one way of converting it. I know that there are 1,000 meters in a kilometer. So if I multiply by 1,000, I'll now convert to meters. Now I have meters per hour. But that's not really good. So why don't I do this? Why don't I say that in 1 hour there are 60 minutes? Well, now I've gotten my conversion to meters per minute. But I still want meters per second. Well, in 1 minute, there are 60 seconds. So really, the long and short of this, if this can kind of follow, you have to take 100 times by 1,000 and then divide by 60 twice. And if you do that, 100 times by 1,000, divide by 60 twice, I end up getting this value here, 27.777 repeating meters per second. And that would be my speed in meters per second. Right? Really what I had to do is I had to make more meters than there was kilometers, because there's 1,000 meters in a kilometer, right? But then that was then per hour, and there are many, many, many seconds in an hour, so I had to reconvert that again. So if I lost you on this step, again, this is the beauty of the asynchronous classroom. Call me over. I'll try to help explain it again. Or rewatch this little video, see if that unit conversion makes sense. One of the things that I'm trying to do here is to like cancel different units with each other. And if you've ever seen that before, it's a really clever way to keep track of things, because the units that are left now are meters over seconds. So I think I'm now ready to do my math, only I'm going to need to go to a new page. So here's my formula. D equals VIT plus 1/2 AT squared. So I'm going to do this twice. My velocity initial was 27.7 repeating, and I'm going to use that number, the entire number. And I'm going to multiply by my time, which was 2.3. Then I'm going to add 1/2 of a negative acceleration. So I'm going to use this one right here, the 7.37. I'm going to use the wet surface one. So we're going to multiply by negative 7.3, and make sure you get the whole value, negative 0.37616. There's actually a way to store these values in most calculators. And if you know how to store a value in a calculator, that's fantastic. If not, this would be another great time. Pause the video, ask Chris. So I'm going to type this in now. I'm going to do 27.7 repeating times by 2.3. I'm going to add 1/2 times by negative, that whole value, 7.37616, and times that by 2.3 squared. And I've got a stopping distance of 44 point, and I'll keep a couple digits here, 3, 7, 8, 9, etc. I often will write little dots afterwards to indicate that I'm going to like save those values. And what would be a great idea is if you know how to store this in your calculator, store it as like letter A, for example, and we'll save that. because that was, I believe, the wet stopping distance. Now we have to do the dry stopping distance. I might have them backwards, but it really won't make a difference because you use the same formula. D equals VIT plus 1/2 of AT squared, and you're still plugging in all these values. 27.77 repeating, still a value. The time was still 2.3. The only change now is we're using the different acceleration rate, which was 7.10184. Negative 7.10184. And that'll be multiplied by the 2.3 squared. And so I'm going to do that now. So exact same calculation, 20.77 repeating times by 2.3 times 1/2. Don't forget the negative number on the acceleration, 10184, and times by 2.3 squared. And this time I got a stopping distance of 45.1045, and I'll put ... And I'm going to store that as my answer B. Again, if you don't know how, just ask. If you have a graphing calculator, I should be able to show you how. Well, for the last step here, it wanted to know the difference in stopping distances, right? So how much worse is it or better is it between wet and dry? Just subtract your numbers. So take the one number, the 45.1045 number that you have hopefully stored, subtract the 44.3789 number that you have stored, and I got a difference of 0.7255, etc. And now it's sig dig time. It looks like we're limited to 2 sig digs based on this time value. So 2 sig digs means we get a difference of 0.73 meters. Now you might think, less than a meter? But hang on a sec. I mean, 1 meter of stopping distance could definitely be the difference between an accident or no accident, between wet or dry conditions, right? So that makes logical sense. Now, this is a great example here. I went through a pretty challenging question with numbers all over the place. Even if you did understand this, I think you should re-go through this example one more time, because I think that would be worthwhile and productive to just re-watch it, right? Why not? I'm keeping track here of the time. It's only been 32 minutes since you started watching this video, if you haven't paused. So we should hopefully have lots of time left over. So re-watch the example, or like I said, call me over and ask. The beauty of this, and I won't say this every time we have a lesson, but I'll point it out, is that you can pause, you can rewind, right? You should do that. Okay. We've got one last example, but this one's actually a pretty challenging one, and so I want to do this one together as a group. And so if you get up to this point right now, that's fantastic, right? Maybe rewatch the lesson for a bit. I'm going to finish our class today with this last example because this one's a bit of a challenging one. What we've got, maybe what I can even suggest is try it yourself before I get there. We've got a velocity initial of 97. We've got an acceleration of 26. I should put units on here. I shouldn't be lazy. And we've also got a distance of 3.2 kilometers. I'm going to do a quick conversion to make that 3,200 meters. And what we're being asked to solve for is time. And this is a good puzzle because if you look back through the formulas here, there is a formula that involves all of these, but it's challenging to solve. You can use the formula VIT plus 1/2 AT squared, make that equal to distance. But what makes this one challenging is there's time in more than one spot. So maybe why don't I leave you with this? Rather than me do all the work for you, I'd like you to try to figure out on your own. See if you can try to troubleshoot how you're going to isolate time when there's more than one variable. There are 2 common ways of doing this that I can think of. Maybe there's more. So that's your challenge. Try to work on this for the next little while, and I'm going to try to end the class, or if I don't end today's class, I'll begin the next class with this final example. So thanks for watching the first video. I hope this was useful. Like I said, the runtime's just over half an hour, so that should leave you lots of time to rewatch and look this over. And more than anything, ask me for help. That's why I have a job. That's why we're here. So, all right, thanks for watching, guys.